Today we're going to talk about inverses. Okay, so what is an inverse? We've seen inverse before. An inverse switches inputs and outcomes. In other words, it switches domain and range, or very simply, it switches x and y. So as far as ordered pairs are concerned, an ordered pair xy would become yx, right? The x and y would switch. Graphically speaking, if I had a function that just was this very simple function, and I wanted to show its inverse, I could switch the xy's. So negative 4, 2 would become 2, negative 4. 0, 6 would become 6, 0. And 10, 10 would become 10, 10. So the inverse would look like that. So this would be, and the notation for inverse is that little negative 1 that we saw with trig inverses. I still dislike that notation because it implies reciprocal when it actually means inverse, but that is the notation that was chosen for inverse. So f inverse of x. If you look at this really carefully, and if I put in the line y equals x, you'll notice graphically that the inverse is actually a reflection over the line y equals x because I've switched x and y, so the line y equals x is sort of a line of symmetry if they're both on the same graph at the same time. Okay, algebraically, what happens? Well, algebraically, if I have, instead of writing this as f of x equals x cubed, I write it as y equals x cubed. Then I just switch x and y. So the inverse would be x equals y cubed. That's not our usual way of writing things, so I'm actually going to take the cube root of both sides to show that y would equal the cube root of x. That would be the inverse. So I could write that as f inverse of x is actually the cube root of x. So cubing and cube rooting are inverses of each other. And that should make sense because they undo each other. Keeping with that undo mode, in order to algebraically show that two functions are inverses of each other, we have to show two things. So here's the proof, the algebraic proof, that two functions are actually inverses of each other. We do f composed with f of x and f inverse of x composed with f of x and show that they each equal x. So they undo each other to the point where they just make x. So f of f inverse of x would say I'm going to substitute f inverse, so the cube root of x, into this. So the cube root of x cubed, well, that's just x. F inverse composed with f of x would say to substitute f of x into f inverse of x. So the cube root of x cubed. Well, that's also x. So QED, there's the proof. They are inverses of each other, algebraically speaking. Right, here's a fact. Every function has an inverse, but the inverse is not always a function. So let's take one of our nice basic graphs, the top of a circle. I'm going to use a circle of radius 2. So the square root of 4 minus x squared would make this nice top of a circle. Notice that its domain is negative 2 to 2, and its range is 0 to 2. The inverse, so let's just do this graphically. So this is the point negative 2, 0. So 0, negative 2. 0, 2, so 2, 0. And 2, 0, so 0, 2. So the inverse is going to be here. If we do the vertical line test, we notice that this inverse is not a function. Okay, so It has an inverse, but the inverse is not a function. If I were to find it algebraically, let's see, x equals the square root of 4 minus y squared. So square both sides. X squared equals 4 minus y squared. I'm going to add y squared and subtract x squared. So y squared equals 4 minus x squared. And square root both sides. So y equals plus or minus the square root of 4 minus x squared. Looks like we would have gotten the entire circle, but we're also reminding ourselves that if we cannot solve uniquely for y, we don't have a function. So this isn't a function. By the way, this implies that we would have drawn the whole circle. But remember that when we do an inverse, the domain and range switch. So the domain of this is only from 0 to 2, and the range is from -2 to 2. So we're seeing that the domain is only from here to here, and the range from here to here. So we weren't allowed to draw the other half of the circle based on the original function. But my point here is that this function had an inverse, but the inverse is not a function. Okay, so how could we tell if the inverse was going to be a function? We have something called the horizontal line test. Remember, the vertical line test determines whether an original equation actually is a function. So if we're going to switch domain and range, switch x and y, it should make sense that a horizontal line test will determine whether the inverse is a function. So obviously f of x is x equals x cubed is a function. It passes the vertical line test, but it would also pass a horizontal line test. I'll put a horizontal line out here. Which means that if I switched all the x's and y's, the inverse will be a function. Okay, here's g of x, which is the absolute value of x. If I try to do the horizontal line test here, notice I'm not passing a horizontal line test, which means when I switch all the x's and y's and redraw this, I won't pass a vertical line test. So the inverse of f of x actually is a function, but the inverse of g of x is not a function. We use words like 1 to 1. So if a function is 1 to 1, meaning 1x, 1y, right? For each x, there is only one y, and for each y, there is only one x, then its inverse will be a function. Okay, in this case, for each x, there's only one y, but for some of the y's, there are more than one x, so that's why the inverse of g of x is not a function. Okay, let's put all the pieces together. We have f of x equals 1/2 x minus 3. I'm going to graph that. Okay, so -3 up 1 over 2, up 1 over 2, up 1 over 2. We'll draw that. Okay, so that's f of x. It passes the horizontal line test, so its inverse will be a function. We could either find it by algebraically rewriting this or by swinging these points around. So 0, -3 would be -3, 0. 2, -2 would be -2, 2. 4, -1 would be -1, 4. 6, 0 would be 0, 6. So we've got this would be f inverse of x. Algebraically, I could find it by saying x equals 1/2 y minus 3, x plus 3 equals 1/2 y. Multiply both sides by 2. So y equals 2x plus 6. By the way, 2x plus 6, 2, 4, 6. This is what I did draw, 2x plus 6. F inverse of x is 2x plus 6. And again, if I put in my y equals x line, I can see that there's a reflection, right, across y equals x. So those are all the pieces put together for inverse function.